So the title of the module, Basic Materials of ODEs with First Order, Second Order ODEs. Yeah. So those ODEs are pretty simple. So many of you, based on my experience last time, many of you learned that, okay? How to solve those relatively simple first order, second order ODEs. Yeah. So that part, the review, yeah. So because I need to go through that basic part. So for you, yeah, just you may forget some of the techniques, yeah. So you can treat it as a review. But another important part, yeah, because when you learn the ODEs, you solve the math equations. Yeah. So you may not work on many word problems, right? So for this module 1, we will focus on the word problems. So you need to practice the analysis part, yeah, how to set up the equations. So that part also pretty hard, yeah, not very easy. You need to practice, okay? So you focus on that part. Solving equations, you treat as review, yeah, because you did that before, okay? When you learn ODE, you already learned that. Yeah. All right. Yeah. Decay model. So the first type of word problems using the decay model. Yeah. So let me explain this model first. Yeah. 8.1, radioactivity. Yeah. Case study. Yeah. All right, so let's start. Yeah. First, I want to explain the general problem-solving procedure. Yeah. So in this class, basically what we are going to do, solving engineering problems, real-world engineering problems. Yeah. The objective, yeah, develop problem-solving skills for the engineering problems. Okay. Yeah. So what's the engineering problem? Yeah. The description like this: an application problem usually with the physical nature. Physicists, we need to use a lot of knowledge in physics knowledge, okay? Yeah, you will see, yeah, most of the background knowledge we are going to use from physics, okay? Yeah, all right, yeah, physical nature. All right. That 4 blocks, yeah, for the whole procedure solving this kind of problems, we go through these 4 blocks. Let me explain one by one. Okay? The first block, yeah, physical system. When we start, yeah, so we are given a physical system. Okay? Yeah. The background of the problem, yeah, physical system. All right? So we need to know many physical concepts. Okay? Yeah. You need to recall, okay? Yeah. So in your middle school, high school, a lot of concepts. You need to use the knowledge from there, okay? Physical concepts, yeah. But from my side, I will explain those basic concepts, okay? So, get yourselves familiar with those concepts first. Yeah. All right. Yeah. To understand the basic meaning of the given engineering problem. Yeah. This part, you need to have a very good understanding before you can work on it. Yeah. So this part, so you need to spend quite some time try to understand. Okay. Yeah. Yeah. All the concepts, yeah, appeared in the question, yeah, you need to understand. Question? Yeah. All right, good. Yeah. Second block. Yeah. Second block. After that, then mathematical model. You need to start solving it. How to solve? Very important step. Mathematical modeling step. Modeling. Yeah. So what's that modeling stage? We need to know appropriate physical laws. Okay? For example, Newton's laws. Okay? Newton's laws, right? Yeah, so you're familiar with Newton's laws. Hooke's laws. Okay? Many physical laws we need to use. Large number, yeah, not too many, yeah. Several physical laws, okay? Yeah, we need to use. Yeah. So you use those laws to construct your mathematical model to describe the problem, to formulate the whole problem. Okay? Yeah. Before you can solve it, yeah, you need to do preparation. Okay? So this step also important and not trivial. Yeah. Okay? Yeah. Second block. Third one. Yeah. Yeah. So the model, so what kind of model? Too abstract, right? So basically, we use differential equations to represent our model. Okay? Yeah. The form of the model, differential equations. That's the, give you the specific form of the model. Okay? Yeah. Differential equations. Yeah. ODE or PDE, yeah, partial differential equation. Yeah, last semester I didn't have chance to cover PDEs. Yeah. This semester I tried to squeeze some time to cover. Yeah. Because last time it was my first time to teach. Yeah. Yeah, I need some experience. Yeah. So this semester I tried to, based on my experience from last year, to do some adjustment. Yeah. Because some important knowledge I couldn't find time to cover. Yeah. Yeah. So I want to make sure, try to focus on the most important part. Yeah. All right. Yeah. So that's the second block. Third block, mathematical solution. You need to solve the ODEs. Yeah. ODEs, the model, find a solution. Yeah. So then you need to apply the techniques. So this class, we will learn many techniques. Yeah. Some of the techniques you learned before, okay, from your ODE class. You learned it before. Yeah. So we review, but we will learn some new techniques. All right, you need to practice. Yeah. So in 2 tests, there you need to solve, quite some. Yeah. 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 Word problems, yeah. But not all word problems. Yeah. Some equations, approximately 1/2 the equations I will give you as the math formulas directly. Yeah. So you just solve the equations directly. But for the word problem, you need to do a lot of analysis, right? You need to set up equations. Yeah. You need to pick the correct physical laws to, set up equations. Yeah. 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 But I give you plenty of examples in the notes. Yeah. So you won't see brand new questions. Yeah. All the questions appeared in the 2 tests, all old types of questions, old question types, no brand new question types, to be fair, right? Yeah. Otherwise, maybe too hard for you. Yeah. All right. So that's the block number 3. We need to master various techniques on the differential equations to solve, these equations. techniques. Yeah. So these techniques, yeah, we need to learn some very powerful tools, problem solving, mathematical problem solving tools. Yeah. 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 So this semester I tried to allocate a little more time on those powerful tools. Last semester, last year, because I did two most important powerful tools after the midterm, then we didn't have enough time to practice those powerful tools. Yeah. So this semester I tried to make some adjustment. Yeah. Bring one of the two powerful tools before the midterm, okay. One after midterm, one before midterm. Yeah. Then you have more time to practice. Yeah. All right. The last block. After you find a solution, at the end, you need to do physical interpretation. Yeah. Conclusion. You need to make conclusion, right? After you find a solution, then you need to use based on your solutions, you need to interpret some phenomenon. Okay? Yeah. 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 Sometimes you need to explain a little bit. Yeah. So the last step. Yeah. All right. After we get a solution, we explore its properties. Yeah? The solution may have some special properties. Okay? Yeah. For example, so we will solve one, describe the human population. Okay? The population, yeah, not necessarily for human, for fish, so several different species, yeah, population, yeah. What's your conclusion, right? Yeah. So based on that, so we want to get some properties out from the solution. So we do some discussions. Yeah. Yeah. So that's the last step. Graph it. Sometimes we want to view our solution visually. We want to get a visual view of our solutions. Yeah. Because if you look at solution in the math formula, you may not be able to see some hidden properties, right? Yeah. So in that situation, you may need to draw graphs of your solutions to help you see some important properties. Yeah. All right. Yeah. All right. Find the values. Yeah. Solution usually it's a function, right? A solution of a PDE usually it's a function. Okay. Differentiable function. Yeah. But for that function, we are interested the function values at some special points. So you need to find the values at those special points. Okay? So you do at this last step. Interpret in physical terms. Yeah. Okay? So this is the general procedure description. Okay? Just give you an idea. Yeah. Well, you need to solve a word problem with engineering background. Yeah. So typically you need to go through these 4 steps. Yeah. Okay. Yeah. All right. Yeah. So after this general description, let's work on our first concrete problem. Okay. Concrete physics problem. Okay. Yeah. Number 1. Yeah. So here I want to say for us, yeah, because for this class, this step regarding the techniques. Yeah. So our main focus is here. Okay. Our main focus is here. Yeah. Although the analysis steps before the solution step, analysis step, also important. Yeah. But usually I give you several examples. So you just use my examples. Okay? You try to based on your understanding, you need to apply the thinking analysis from old examples and using analogy sometimes to work on the new questions. So that's the, these two steps. Then the main problem solving work is the block number 3. So most of your work, okay, block number 3. Yeah. All right. Yeah. Problem 1, radioactivity. Context. Okay. Yeah. The problem. That context. Yeah. All right. So here we need to, I help you recall some basic physics knowledge a little bit. Yeah. Recall a little bit. Yeah. All right. Yeah. First, let me give you the question first. Given 1 g, 1 gram of the radioactive substance, radium, so notation is this one. Yeah. Notation. Okay? The radium notation. One of the isotopes of that substance, radium substance. Okay? Yeah. Yeah. All right. So I will explain the details. Yeah. After I give you the question, I will explain the details. Yeah. Yeah. So do not get scared. Yeah. All right. Find the half-life of the radium in years. Half-life concept. Okay. Here, we need to understand half-life concept. Yeah, I will explain that. Some of you know it. Yeah. But make sure everyone knows it. The meaning, yeah, I will explain this half-life concept. All right. What's the half-life? The definition. The time in which half of the given amount of radioactive substance will disappear. Here, the amount, given amount, 1 gram. Okay? Given 1 gram. Yeah. Radium, yeah, the substance. Yeah. Radioactive substance. Yeah. Due to the radioactivity, we know the amount of radium, that amount going down. So when the time goes by, yeah, amount of radium, yeah, disappear. Yeah, disappear means it will be changed to other substance. Yeah, changed to different substance. Yeah, disappear. Okay, the original substance disappears because there is some equation, chemical equation. So by the radioactive property, it will change to different substance. So the original substance, you cannot measure same amount of substance. Yeah. All right. So disappear. The half-life. Yeah. How much time do you need to reduce the amount of this 1 gram V radium to 0.5 radium? 0.5 gram radium. 1/2 amount. 0.5 gram. You need a certain amount of time. Okay? So that time period, we define it as the half-life. Half-life. Okay? That concept. All right? Yeah. By the physical law, yeah, we need to use some physical law. Okay? So you can see step 1, we try to understand all the concepts appeared in this question. Step 2, we need to establish some mathematical model. So we need to use some physical law to establish that model. All right. So what physical law? We need to use some physical law here. The physical law is the time rate of change. Yeah, time. Yeah, here. Yeah, so here let me explain. slowly, yeah, especially at the beginning. I want to slow down a little bit. Yeah. All right. So at the beginning, all right. So here, we need to use y of t. You know it's a function. Y is a function of time t. Okay? Y of t to represent the amount of radiant. Amount of radiant. All right? Yeah. Because its value changes, you know, according to the time, yeah, based on the time. Yeah. 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 So it's a function of time. Yeah. The amount decreases. Decay, the decreases. Okay? Y of t, it's a decreasing function with respect to variable time. So that's the amount function, y of t. Yeah. Then, because it is changing, so there is a rate of change concept. Change in what rate? Right? A function changes in certain rate. How do we represent rate of change? In calculus, we use derivative, the y prime derivative to represent this concept, rate of change. Okay? The rate of change of a function, so the description is the derivative of that function from calculus. Okay? Yeah. All right. Here you need to use the calculus knowledge. Okay? I do not have time to, review some basic knowledge in calculus. Yeah. But if you have a question, so you can ask me. Yeah. I will explain. Yeah. All right. Yeah. All right. Yeah. So here, this is another way to write derivative. We know we have several different notations to write the same concept, derivative, right? One is y prime of variable t. Another, we use differentials, dy over dt. dy, that's the differential concept. So here, based on my experience, last year, many students, they didn't feel comfortable about the differential concept. Yeah. Ask yourself if you feel comfortable about this differential concept. Differential. Yeah. Because later, when we solve some special questions, we need to use this differential concept. Okay? Yeah. So here, the relationship between the derivative concept and the differential concept. Okay? dy over dt, two differentials. Okay? Differential of the y function and the differential of t variable. Two concepts, differential concept. In calculus, you need to learn differential, but last year, most students in the class, they felt very hard to understand this differential concept. Now, later I will use some PowerPoint slides to explain that differential concept. Okay? Yeah. It's a powerful venue, yeah. So powerful way to understand the background. Okay? Yeah. So do not miss that part. But it's a difficult point from last year, yeah, based on my experience last year. Very hard. Yeah. And most students just feel too abstract. Yeah. Hard to comprehend. Okay? Differential concept. Yeah. Yeah. So here I delay. Yeah. I do not explain differential concept here. Yeah. I delay after a few more lectures. Yeah. Yeah. All right. Yeah. So that's one. Yeah. Next. The physical law tells us the rate of change, this is rate of change, is proportional to the original function. That's the statement of the physical law. Okay? Yeah. There is no name for it. Okay? Yeah, some big law, there is some name, right? Yeah. So this is relatively small physical law, so there is no name. Okay? Yeah. But it's a law. Okay? Physical law. Yeah. How to get it? You may ask me how to get it, right? Yeah. So many physicists, they do experiments. Okay? Do a lot of experiments. Yeah. Then look at the data of the experiments and try to find some rule. Yeah. Yeah. So then at the end, they observed this law. Yeah. Physics, most laws derived from experiments. Okay? Yeah. From experiments. Physical law. Okay? Yeah. Yeah. So we just use their experiment result for this physical law. Okay? Yeah. All right. So for the radioactivity, so this model, this type of questions, it follows this equation. Okay? That's by physical law. Okay? Yeah. Yeah. All right. Yeah. So we're given the physical law is there. We just use the existing physical law. Okay? We do not need to discover it. Right? So for this class, we never need to discover any physical law. We just use the existing physical laws. All right? Yeah. So this is the first one. First physical law for this class. All right. The constant is given. Yeah. The constant K equals 1.4 times 10 to the negative 11, the unit, 1 over second, 1, okay? Reciprocal, 1 over second, okay? Yeah. Why 1 over second? If you look at this derivative, dy over dt, dy over dt, dy amount, okay? Yeah. dt, the second is at the denominator, right? Yeah. So 1 over second. 1 over second, that's the unit for this constant K. Constant K. Yeah. Because dy is unit the same as y, unit of y, right? dy. dy differential, you can use the difference. Differential closely related to that difference of two y values. So that's the same unit as y, right? So the y unit here, y unit, two sides can be canceled out. Then the unit for K is the same of unit 1 over t, t time second, okay? So that's the reason K, constant K, use this 1 over s second, 1 over s as the unit. Okay, yeah. Physics, we use this way to figure out the unit, our quantity. Yeah. Sometimes a little tricky to figure out the correct unit. Yeah. All right. Yeah. K is known, okay, from experiments. Yeah. Those physicists, they do experiments. They, based on their experiment results. So this constant K is given to us. Okay? For radium, you use this constant. Okay? For a different radioactive substance, you use a different constant K. Okay? Yeah. All right. Yeah. And the radium here, we are using this specific isotope of radium. Radium has several isotopes. Okay? So this one is, so this class we will use 2 different isotopes. Yeah, okay.
Will we always be given K, or will we have to look it up?
Based on the questions. For some question, you are given the K.
Okay.
But some question you give other data, but you need to calculate the K. Okay? Yeah. Calculate the K based on other information. Okay? Yeah. All right. The background. Yeah. First, let's understand the half-life concept. Another time, after I give you the definition, let's understand half-life concept another time. Yeah. The general meaning of the half-life, the time required for a quantity of substance to reduce to half of the initial value of that substance. Yeah. That's the general meaning. Okay? Yeah. Half-life. Okay? All right. Yeah. So this time, we use this general description. So you can see for all the substance fit in this description, we can use half-life concept to describe it. Okay? Then we can do things very general. Very general. Yeah. It's not necessary connect to the radioactive substance. Yeah. Although this concept came from radioactive substance. Its origin came from radioactive substance. Okay? Yeah. Why people made this concept, right? So its origin from radioactive substance. But after people define this concept, then they feel, well, we can use this concept not necessary only for radioactive substance. We can extend it to many other non-radioactive substance. Okay? Yeah, there are many similar phenomena. Okay? The phenomenon satisfies the decay model. Okay? Because this radioactive substance, it satisfies certain decay model. But it's possible some other phenomenon also fitting this decay model. Can we use half-life we extend half-life original meaning to cover, more phenomena. That's the idea. Okay? Yeah. So that's how human develop their knowledge. Okay? Yeah. So the knowledge people develop. Yeah. In the long history of mankind, it's a very common way. Yeah. All right, so here the term commonly used in nuclear physics. Yeah. Radioactive substance appears in nuclear physics, right? Yeah. So that part of knowledge in physics, nuclear physics. Yeah. All right. Commonly used describe how quickly unstable atoms undergo radioactive decay. Yeah. So so that concept used in two cases. The first case, unstable atoms. Second case, stable atom. How long? Stable atoms. Yeah. For stable atoms, we can also use half-life to describe some changing property, right? The property, how to change that property. For stable, it means it changes slowly, in a very slow way, but still changes, right? Unstable means it changes very fast. Decay very fast. Okay? The half-life, the number used for the half-life is a big number. Okay? Stable atom, the half-life, that number, stable, opposite, stable, the half-life is a big number, right? Yeah, because stable, after a long time, it reduced to half. Unstable, the half-life is a small number, very small number. Okay? So after short period of time, the original amount is reduced by half. That's unstable. Yeah. So we can use this concept for, those two cases. Yeah. All right. Next, the term is also used more generally to characterize any type of exponential decay. Yeah. So here, this statement, this one tells us we can extend this concept out of the nuclear physics. Yeah. Out of nuclear physics. Okay. In some other different physics, if the pattern, if the trend, the pattern of change, if they have the same property, follow the same property, then we can use this half-life concept to describe it. Okay? Yeah. Later we will see a different example. Yeah. The context is completely different, but we can still use the analogy of the half-life. Yeah. We extend it. Yeah. Analogy of the half-life concept. Yeah. All right. Yeah. Property. Yeah. All right. So here, the half-life is constant over the lifetime of an exponentially decaying quantity. Yeah. Here you can see every time when we have some phenomenon with the exponential decay property. Yeah. So anyone wants to ask what's the exponential decay? Exponential decay? Yeah. So we will see that. It's here. Yeah. If you have question about the exponential decay, next slide we will see that. When we exponential decay, the decay model is closely related to exponential function. You know exponential function, right? Yeah. Follows that exponential function. The decay function is an exponential function. That's simple, straightforward. Yeah. Exponential. Yeah. So when we do the solution, you will see that exponential function. So exponential decay. So any phenomenon with the exponential decay, we can use this property. Okay, so we can use the concept to describe the decay property. Okay, so decay property, half-life, this concept to describe the decay property, constant over the lifetime of that exponential decaying quantity. Okay. Due to any reason, the function of certain quantity, a general function of certain quantity, it changes following an exponential function. So if you have some phenomenon can be described in that way, then we can use the similar concept. Okay? Yeah. All right? Yeah. So here for this class, so I try to move at the beginning, not too fast. Try to, help you adjust your thinking in a special way we will use for the whole class. So we will do a lot of thinking, a lot of analysis. Okay? Because eventually you need to solve these problems by yourselves. Okay? You need to solve these problems by yourselves. So the good understanding is very important. So here I try to, show you different aspects of the thinking in solving these problems. All right. So let's continue. All right. Background, more background understanding. Yeah. Understand the radium substance. Yeah. So we need to understand more about the radium substance, right? Yeah. So what's the meaning of this 88? What is that meaning of 226? Right? Yeah. We need to get a little more knowledge. Yeah. Yeah. So let's learn that part of knowledge here. Yeah. All right. So first, yeah, I want to show you a picture of pure radium, silver white. Yeah, this picture. Okay, the radium. Okay, pure radium. Yeah, like that. The picture. Okay. All right. Its atomic number is 88. Atomic number, that concept. 88 means it's atomic number. Yeah. But what's the meaning of atomic number, right? Yeah. Recall what you learned in physics in your high school, yeah, or middle school, yeah. So, yeah. What's the atomic number? Good. Yeah. Good. Yeah. Excellent. Yeah. Number of protons. Number of protons equals 88. That knowledge, okay? All right. Yeah. Next, yeah. So here, let's look at the periodic table, okay? Yeah. Yeah. So pretty complicated. Yeah. So I do not want to go through. Yeah. Yeah. Well, we got too much time. I don't want to spend too much time on this table. Yeah. But you can see the radium is here. The radium, 88. This number, okay? Yeah. Radium. Yeah. Then let's understand that 226. The meaning of that 226. 226 minus 88 equals 138. So that's the number of neutrons. So the sum of the protons, number of protons, and the sum of, of the number of neutrons. Yeah, the sum of these two numbers, okay, protons and neutrons, that total 226. Okay? Yeah. So that's the meaning. Yeah. Okay. All right. Then there is another isotope of the radium, 226. Isotope. You can see they have the same number of protons, 88. That part the same, but the number of neutrons for these two isotopes are different. Now, for this one, there are 136 because two fewer. The total number two fewer. So there are 136 neutrons in this isotope of the radium. Okay? Yeah. All right. Then we also need to understand, yeah, we want to compare these two isotopes of the radium. Yeah. And the number of protons determines the chemical property. Okay? That means these two isotopes, they have the similar or same chemical property. Yeah, because same number of protons. Okay? Yeah. But this number different. Yeah. Number determine the physical property. So these two isotopes, they have the different physical properties. Okay, due to that, number of neutrons different. Okay, yeah, chemical properties, physical properties. Yeah. All right, yeah. So, yeah. Then, all isotopes of radium are radioactive. Yeah. So, for this substance, for this radium substances, all of its isotopes are radioactive. It has this property. But for some other substance, later we will learn carbon substance. Then this property is not true. So that some of the isotopes are radioactive, but some of the isotopes not radioactive. Okay, for different substance, carbon. Okay, carbon. Yeah, yeah. So there are 3 different isotopes. Yeah. So the property is quite different. Yeah. Our third example, we will use that carbon isotopes. Yeah. All right. The most stable isotope of these 2 isotopes, most stable being radium-226. That one, most stable. Because its half-life is a big number. 1,600 years. It's quite long. Yeah. After 1,600 years, then the amount of that isotope of the radium is reduced to it's half of the original amount. Then it's stable. Yeah. So we. Yeah. But this isotope is not stable because its half-life is very short, unstable. So its half-life is 3.6 days. Yeah, 3.6 days. See? Yeah. How big is the difference? Okay? Yeah. So here you can see, due to these 2 numbers different, yeah, their half-lives are quite different. So the half-life, this property, they have different physical property, right? One is very stable, yeah, the half-life very long. Another, unstable, half-life very short. Yeah, so they have different physical properties. Yeah. All right. Now, so let's work on the solutions. So here you can see we spend a lot of time to understand the background. Yeah. Yeah. Otherwise, you won't feel comfortable, right? So if you have a lot of things unknown, so when you work on the problem, you do not feel very comfortable. Okay? Yeah. So you don't have the confidence. Yeah. But after you know all the necessary related background information, then you feel more comfortable. Yeah. Okay? Yeah. So you can apply your knowledge to solve. Yeah. So today we don't have, yeah, but still the story, probably I couldn't complete the whole story today. Yeah. All right. So beginning, let's work on the solution. Yeah. At the beginning, so this toolbox, I use it to, represent our problem-solving skills. Yeah. So at the beginning, at this point, it's pretty empty, right? Yeah, because you do not have many tools in your toolbox, okay? Problem-solving toolbox. Yeah. But after this class, yeah, so I hope you have many tools in your problem-solving toolbox. Okay? Yeah. So you know how to solve many different types of problems. Yeah. But we need to start with this kind of empty toolbox. Okay? Yeah. So the first question, yeah, what tool can we use? We do not have many tools. Yeah. But we have some background knowledge, right? Yeah. So when you come to this class, yeah, so you need to meet certain prerequisites. Yeah. So that's the background knowledge. Yeah. Yeah. Here the background knowledge is calculus. So at this point you have the calculus background knowledge you can use to solve this problem. Okay? All right, so let's use calculus to solve this, our first problem. Yeah. All right. Set up an equation. Yeah. Set up equation. Yeah. Remember the physics law, right? it's given, previous slide. Yeah. So it's very easy to set up equation because that equation is given. Okay? Yeah. So this is the equation. We need to solve this differential equation. Very simple differential equation. Okay? Yeah. Yeah. So here, I do not assume you have any problem-solving skills at this point. Yeah. Although some of you know how to solve. Yeah. I believe. Okay? I believe many of you know how to solve this one. Yeah. But here, in order to make my story, right? Yeah, I need to, go through the whole process, of my story. So here, I do not assume you have any problem-solving tool in your toolbox. Yeah. All right. Yeah. So let's look at how to solve it. All right. Yeah. Here, this y function. Yeah. It's meaning the amount of radium substance. Yeah. It changes. Yeah. So our goal, we need to find this y function, y of t function, the explicit form of the y function. That's our goal. Yeah. All right. Because goal is this half-life. After we can find that, so then we can calculate the half-life. Yeah. So we want to determine this function first. Yeah. So here we need to solve this very simple. This is the first order differential equation. Probably the simplest. Yeah. Yeah. People may argue. Yeah. But it's a simple differential equation, first order, ODE. Yeah. All right. So here I want to do some analysis. Yeah. We want to solve this equation. So let's look at this general equation. dy over dt equals a c constant times y. Yeah. So we want to see how to solve yeah, this ODE, c not equal to 0. Okay? Yeah. We assume c non-zero. All right. So then, if c greater than 0, it's a positive number greater than 0. Yeah. What's the meaning? The derivative equals positive constant multiply the original function, positive function. Okay? Yeah. Yeah. So here, yeah. Because so this y of t, that's the amount of substance. Amount of substance is a positive number, right? Yeah. Amount of gram. Yeah. Certain number of grams. Okay? Yeah. It's a positive number. Positive c times positive number. Its derivative is positive. That means this function is increasing, right? The function value becomes larger and larger. In calculus, we learned this property. If a derivative of a function is positive, it's increasing, right? Do you have that basic knowledge? If the derivative is positive, what's the derivative? Derivative corresponds to slope of the tangent, right? Suppose you have a curve, right? Yeah. At any point you can draw a tangent line, right? Yeah. The derivative means the slope theta here, the tangent theta, it is the slope. Sorry? Yeah. Yeah. No? Why? You freeze. Oh, that's bad. Yeah. Sometimes I got a freeze problem. Then, oh, my remote control doesn't work. Yeah. So near the end, yeah, but good thing is, it's near the end, only 5 minutes left.
I have a question.
Uh-huh.
Why did we negate the negative sign on the side?
Just opposite, okay? Decreasing, yeah. Because the derivative is negative, that means the slope, yeah, the tangent line like this, the slope is a negative number, right? So you're going down, yeah. Positive going up, okay? Going up, the function becomes larger and larger. Function becomes smaller and smaller, okay? Yeah, so the derivative tells you that property. Yeah, all right, yeah, good. Yeah, all right, yeah. Yeah, for the first class, I move very slow, yeah, but I try to, slowly, after you feel comfortable with the whole environment of this class, okay? So I try to move a little faster. Yeah. All right, so let's stop right here.